Today we're going to look at section 7.5, basic concepts of probability. It all comes down to this. The game of Monopoly that started hours ago is in the home stretch. Your sister has the dice, and she rolls a 4, 5, or 7. She'll land on one of your best spaces, and the game will be over. How likely is it that the game will end on the next turn? Is it more likely than not? How can we measure that likelihood? Well, this section addresses the question by introducing a way to measure uncertainty. Now, introducing probability. Uncertainty is also, by definition, a nebulous concept. In order to put enough constraints on it that we can mathematically study it, we will focus on uncertainty strictly in the context of experiments. Call it experiments or processes whose outcomes are unknown. The sample space for an experiment is a collection of possible outcomes. When we want to talk about the likelihood of a particular outcomes, we sometimes group outcomes together. For example, in the Monopoly example at the beginning of the section, we were interested in the roll of 2 dice that might fall as a 4, 5, or 7. A grouping of all outcomes that we're interested in is called an event. In other words, an event is a subset of the sample space of an experiment. It often consists of the outcomes of interest to the experimenter. Once we have defined the event that interests us, we can try to assess the likelihood of that event. We do that by assigning a number to each event called the probability of that event. And we denote that like this. Probability of event is a number between 0 and 1 inclusive. The probability of an event is 0, then the event is impossible. On the other hand, if an event with probability 1 is certain to occur, in general, the higher the probability of an event, the more likely it is that the event will occur. George is about to conduct an experiment that consists of flipping a coin 4 times and recording the number of heads. Decide if these probabilities are equal to 0, equal to 1, or somewhere in between. So what is the probability that the number of heads is less than 5? Well, he's flipping the coin 4 times, so the most number of heads we can get is 4. So that probability is going to be 1. What is the probability that the number of heads will be less than 4? Well, it could be 0. It can be greater than or equal to 0, but it has to be less than 1. Because since we're flipping 4 times, if the probability is 1, that would mean that we got all 4 heads. So it's between. And what is the probability that the number of heads is greater than or equal to 5? And this, of course, would be 0. So we have 3 ways that we can assign probability. Probabilities of events that are certain or impossible are easy to assign. They're just 1 or 0, respectively. What do we do about those in-between cases for events that might or might not occur? There are 3 methods to assign probabilities that we can choose from. We'll discuss them here in order of reliability. Now, first, we look at theoretical probability. The theoretical method gives the most reliable results, but it cannot always be used. If the sample space in an experiment consists of equally likely outcomes, then the theoretical probability of an event is defined to be the ratio of the number of outcomes in the event to the number of outcomes in the sample space. So our formula is, for an experiment whose sample space S consists of equally likely outcomes, the theoretical probability of event E is the ratio, the number of outcomes in event E over the number of outcomes in a sample space. Okay. So you're about to roll a fair, meaning that each face has an equal chance of landing up, six-sided die, whose faces are labeled with the numbers from 1 to 6. Find the theoretical probabilities of each outcome. Well, you roll a 4. How many 4s are there? There's 1 4. How many dice? How many sides? 6. Roll a number greater than 2. Well, how many numbers are greater than 2? That would be 3, 4, 5, and 6. So 4 of the 6 numbers are greater than 2, and we could reduce this to 2/3. You roll an odd number. How many odd numbers are there? 1, 3, and 5. 3 out of 6, and we could reduce that to 1/2. It is critical that you make sure that every outcome in a sample space is equally likely before you compute theoretical probabilities. If you roll a pair of 4-sided dice with faces labeled with the numbers 1 through 4, what is the probability of rolling a sum of 6 or 7? Use the table below to determine your solutions. So how many different outcomes are there? Well, we can basically run, or how many different possible combinations, or how many different possible outcomes are there? Well, we have them listed here. There is 4 times 4. There's 16 samples, or outcomes in the sample space. How many of them are 6 or 7? Well, there's a 6, 6, 7, 6, 7, 5. The number of outcomes in the event is 5, so our probability of a 6 or 7 sum is 5 over 16. You have a modified deck of cards containing only 3 4s and 5s of hearts. You draw 2 cards without replacing them where order matters. What is the probability of each event? Use a tree diagram to determine the solutions. So we start out here. We could get a 3, a 4, or a 5. So what is the probability of the first card would be a 3 of hearts? Well, we have 3 possibilities there. So 1. What is the probability that the first number has a lower number than the second number? So now, if I take the 3, I'm not replacing it, so I could have a 4 or a 5. Here I could have a 3 or a 5, and here I could have a 3 or a 4. So I have a total of 2, 4, 6 possible outcomes. The number of outcomes in my sample space. The second number is larger than the first card drawn is lower than the second. In this case it is, in this case it is, in this case it is. The number in our event is simply 3. So this is 3, 6, or 1/2. One of the cards one of the cards drawn is a 4 of hearts. So we have 6 possible. So this here is 1 with a 4 of hearts. There's another one, and there's another one, and there's another one. Matter of fact, let's do this. We can go here and here, here and here, here and here, or here and here. So there's 4 possible ways to have a 4 of hearts. It'd be 4 out of 6, or 2/3. Next concept we have, or method we have, is empirical probability. Theoretical probabilities are precise, but they can't be found in every situation. If the outcomes in the sample space are not equally likely, then we're out of luck. Suppose you're watching a baseball game and your favorite player is about to step up to the plate. What is the probability that he will get a hit? In this case, the sample space is hit, not a hit. That doesn't mean the probability of a hit is 1/2, since those outcomes aren't equally likely. The theoretical method simply can't be used in this situation. Instead, we might look at the player's statistics up to this point in the season and see that he has 122 hits and 531 opportunities. So we might think that the probability of a hit in the next place appearance would be 122 over 531, or roughly 0.23. When we use the outcomes of previous replications of an experiment to assign a probability to the next replication, we're defining an empirical probability. Empirical probability is assigned using the outcomes of previous replications of an experiment by finding the ratio of number of times in the previous replications the event occurred to the total number of previous replications. Empirical probabilities aren't exact, but when the number of previous replications is large, we can expect them to be close. Also, if the previous runs of an experiment are not conducted under the exact set of circumstances as the one we're interested in, the empirical probability is less reliable. For instance, in the case of our favorite baseball player, we might try to get a better estimate of the probability of a hit by looking only at his history against left or right-handed pitchers, depending on the handedness of the pitcher he's about to face. Now let's look at an example here. Jessie oversees quality control at a factory manufacturing SUVs. Today she's checking the placement of the tail light housing. Of the last 1,000 units off the line, 13 had faulty placement. What empirical probability might Jessie assign to the next vehicle coming off the line having bad placement? Well, of the previous 1,000, 13 of them did. So the last method we look at is called subjective probability. In cases where theoretical probability can't be used, and we don't have prior experience to inform an empirical probability, we're left with one option: using our instincts to guess at a subjective probability. A subjective probability is an assignment of a probability to an event using only one's instincts. Subjective probabilities are used in cases where an experiment can only be run once or it hasn't been run before. Because subjective probabilities may vary widely from person to person and are not based on any mathematical theory, we won't give any examples. However, it's important that we're able to identify a subjective probability when we see it. They will, in general, be far less accurate than empirical or theoretical probabilities. So let's classify each of the following probabilities as theoretical, empirical, or subjective. You have entered a raffle with 500 entrants. Your probability of winning is 0.2%. That's 1 out of 500. So that is theoretical. Your little brother takes the bus to school each morning on the first day of school. You believe the probability that the bus arrives between 7:15 and 7:30 is about 80%. That's subjective. It's the first day of school, so it hasn't happened yet, so we have nothing to rely on. Little brother takes the bus to school each morning. On the last day of school, you believe that the probability that the bus arrives between 7:15 and 7:30 is about 73%. We're going to say this is empirical because we've seen what it's done and calculated how often it did, or that's the assumption anyway. Next concept we look at is called a complement. One of the goals of the rest of this chapter is learning how to break down complicated probability calculations into easier probability calculations. We'll look at the first of the tools we can use to accomplish this goal in this section. The rest will come later. Given an event E, the complement of the event E, denoted with a capital E and an apostrophe after it, in the case of this text, is the collection of all outcomes that are not in E. This language is taken from set theory, which you can learn more about elsewhere. In this text, actually. Since every outcome in a sample space either is or is not in E, it follows that number of outcomes in E plus the number of outcomes in E complement is equal to the number of outcomes in the sample space. If the outcomes in S, the sample space, are equally likely, we can compute theoretical probabilities. The probabilities of E equals N over E over N over S. And the probability of E complement is equal to the number of outcomes in E complement over the number of outcomes in the sample space. Then adding these last two equations, we get the probability of E plus the probability of E complement ends up equaling 1. Thus, if we subtract the probability of E complement from both sides, we can conclude the probability of E is equal to 1 minus the probability of E complement. Keep in mind that we did calculate this based on the outcomes in S being equally likely. So how is this helpful? Well, sometimes it's easier to compute the probability of an event won't happen than it is to compute the probability that it will happen. To apply this principle, it's helpful to review some tricks for dealing with inequalities. If an event is defined in terms of an inequality, the complement will be defined in terms of the opposite inequality. Both the direction and the inclusivity will be reversed. So less than will be changed to greater than or equal to, less than or equal to be greater than be less than or equal to, and greater than or equal to be less than. So let's see what we have here. If you roll a pair of 4-sided dice with faces labeled 1 through 4, what is the probability the sum of the resulting numbers will be greater than 3? And we found the sample space of this earlier. And it was 16. So we want to know probability of E. E being sum greater than 3. Okay, we can look at this real quick. What's the possibilities here? Well, E complement would be sum less than or equal to 3. And rolling 2 dice, I could have a 2 or a 3 as this event. Now, there's only one way I can get a 2, 1 and 1. However, I can get a 3 as 1 and 2 and 2 and 1. So now I have the number of outcomes in the event E complement is 3. So the probability of E complement is simply 3 over 16. Okay? So the probability of E is equal to 1 minus the probability of E complement, or 1 minus 3/16, which is 13/16. And notice how we can use complements to help us find the probabilities. That is it for this section.